Hello, everyone, and thanks for attending the CSP seminar. So this week, we are very pleased to have David Ham as a speaker today. So David is an assistant professor in the business school at the University of Michigan, which he joined in the fall of 2024. Before that, he got his PhD in statistics from Harvard University. His research interests are broadly in causal inference, sequential inference, and adaptive experimentation. And today he's going to tell us about design-based confidence sequences. So yeah, so please join me in welcoming our speaker today.
Small audience, it's okay. Hello. Thanks so much for the introduction, and I'm very happy to be here. I did not expect a small audience, but I actually prefer having smaller groups so we can hopefully have more questions, more discussions in a smaller setting. Just to maybe reintroduce myself a little bit. Yes, my name is David Ham. You can call me David Ham, and I did this project just 2 or 3 years ago in my beloved time at Harvard, where I was doing my PhD. This was actually my job talk for this operations job that right now where I am at is the Technology and Operations Department at Ross. Okay, so today I'm going to be presenting this work, and the co-authors here are Yavor Bashov from the Harvard Business School and Michael and Martin from Netflix. So as you can see straight away, this is actually a collaboration with industry. But I do want to note that this is a fully academic project. We're sort of getting this paper out, but this was a real problem that Netflix wanted to solve. Okay, and actually the results that I will show you here today is indeed already implemented in the Netflix experimentation team. So they're sort of using this to make better decisions in experiments. Hopefully that made you curious, and I want to now explain exactly what this whole project is about. So as a quick overview, I'm going to spend actually a decent amount of time on the introduction and motivation with a bolded emphasis on motivation, because this is actually not a relatively standard framework or setting. So I want to just really take the time to explain why do we even care of doing something like this, and make sure we're on the same page of what we're going to focus on. Then I'm going to actually talk about that existing literature and limitations on the thing that I'm motivated and the thing that we want to focus on to highlight exactly my contributions. Then I'm of course going to show that contribution, and actually not going to spend too much time on the mathematical side, even though the result is completely mathematical, and trying to spend actually more time on the implications and applications as you see here. It is totally okay if I do not reach the end of this, because I'd rather spend more time on questions and hearing what all of you want to say. So I'm just going to go ahead and begin, but please interrupt me with any questions. We have a fairly small group, so I'd love to hear your thoughts. But just so we're on the same page, let's talk about experimentation at the beginning. Hopefully, many of you already don't need this convincing, but just like the title slide says, A/B test and experimentation is super important, okay? And many tech companies use this. So the first question is, why is it important? Let's just use Netflix as an example. One of their biggest sort of million-dollar question is what ranking algorithm or what sort of recommendation algorithm should we show? And it's very complex, okay? The way they answer this question, by the way, is someone, let's say in the marketing team or someone in one of their teams come up with a new idea, okay? Like we'll call this new idea a new ranking algorithm. There are actually many papers out there that are truly just trying to determine what is the best sort of ranking or recommendation algorithm, but let's just say they're trying to use one of those ideas, okay? They still want to ask this very important question. Should we go ahead? We read this in a paper, we heard this from a person. Should we go ahead and deploy this new idea? And I actually very conveniently labeled it B, because in A/B testing, how they actually answer this question and sort of the old ranking algorithm. It's not based on this, but the old ranking algorithm is called A. So that's sort of the control group. And the way they actually test this, clickers acting up, is they do an experiment. Okay, so very concretely, let's just say Netflix has about 250 million people. They would actually experiment on about, let's say, 1%. So this is 200,000 people. These are real members, by the way. And they would just flip a coin, send maybe half of them into this old algorithm in the blue sort of labeled figures above, and the other half into this new algorithm B. Okay, and the important process is that they sort of flip the coin. They're not actually sort of assigning this through some deterministic or some convenient way. So they're very comparable, the group. At the very end of the experiment, they would just run something like a t-test, and they would say A or B is better, finally answering that question I brought up, should they deploy this new algorithm? Okay, so this is hopefully all very familiar. I just wanted to bring us on this common ground. But if you look at this picture, I actually did none of this part here is what the focus of the talk is. In other words, there's a lot of papers that try to determine how to do this part. You can imagine there's 3 or even 4 treatment levels, some adaptive allocation, something to do with smart experimental design. These are all legitimate research questions. I'm not going to focus on. Of course, there's a lot of papers on this side here. This t-test is very simple, it's valid, but you don't even maybe utilize sort of machine learning algorithms or some really strong sort of covariate adjustment estimation procedures. So many research does go into this final part here, the t-test. That is also not the focus of today's talk, okay? So we're just going to assume they can have some sort of way of testing this, and there's already some given coin flip procedure that we know. What today's talk is actually going to be about is sort of this invisible factor that is always running in the background, which is this decision of time. Right? So imagine as soon as I start this experiment, and I've actually worked, interned at Netflix, so I can actually see the analysts starting the experiment. They would have to, before they run any experiment, they have to click this drop-down menu and they have to say, how long should I run this experiment? And typically this choice is completely arbitrary. They'll say 2 weeks, 1 month. I think the other choice is 3 months and 6 months. These are all just human convenient numbers. But this actually has consequences. In other words, if they say, I'm going to run this experiment for 2 weeks, you're going to collect this data from these people across all 2 weeks, and then they can only test at the end of the experiment. Okay, in other words, you'll see this result at the end of 2 weeks. The question that I'm going to sort of tackle is how do we determine this time and when should we stop this? In other words, let's not do sort of just completely an arbitrary number here. And you'll see the consequence. I'm going to convince you why, if they continue their sort of classical framework of just arbitrarily deciding this 2 weeks, they're going to have some loss. Netflix is going to have some dollar cost loss. Okay. So the focus of this talk is actually about this part here of the time. We're going to stop here, see if there's any questions, but just the setup. Great. Okay. So I had actually intended, this is the only slide with a question to an audience, but I'm going to answer myself given the small attendance. But there is a problem of running too long. And I think many of you can actually guess. The problem of running too long, in other words, what happens if I just put this to 1 billion weeks and you just observe their data infinitely? The very obvious answer is there's a time cost, but there's actually more importantly, a customer harm. In other words, let's just imagine the experiment was negative or actually was hurting the customer. If you ran it for 1 billion weeks, you're harming them for 1 billion weeks. And that could really add up. And I'll show concrete examples of this shortly. Just to give you a quick statistic, many of the experiments, let's say by Google and Bing, indeed have these negative effects. And this is just a quick statistic in the paper that I cited. So like 80 to 90% could potentially harm customers. Of course, the flip side, and this is sort of kind of framing this as almost like an operational dilemma. You know, you don't want to run too long, but you also don't want to run too short. And the obvious answer is if you decide to run it for 1 second, let's just take the extreme, you learn nothing, right? You don't even get much data, okay? So this question is very well sort of operationally motivated where you don't want to run too long, you don't want to run too short. Let's get a method to run just long enough so that Netflix is happy, they can learn everything they want, but try to reduce the customer harm. Okay, so this is kind of the sort of the setup of the problem. I'm going to go into some concrete examples. So this is a real experiment that Netflix ran, and for sort of NDA reasons, excuse me, I can't share the exact numbers, but approximately 30,000 units were experimented, and these are on the sign-up page. So you can imagine you go into the sign-up page and they have some A or B version of the sign-up, and they're trying to figure out which version of the sign-up is better as units enter over 2 weeks, okay? And the B or the treatment group, in case you're curious, is they hypothesized that when people are trying to sign up and you're trying to put your credit card, they were thinking that maybe if people run into errors and get these like red messages, they get annoyed, so they stop signing up. So they're hypothesizing if we put an assistance where it sort of detects if your Visa, MasterCard, and also kind of does some nice formatting for you, it would increase sign up rate. Okay, so that was their main idea. As you can see, they try to experiment on everything. They're trying to do every single micro optimization. It turns out that, and I did sort of cherry pick this experiment. I do want to be honest that many Netflix experiments, even the negative ones, are not as negative as this, but there was a negative 20% treatment effect. And I want to be very clear what this even means. It means that if you were in the treatment group, basically because you experimented on, 20% of those people that literally came in to wanting to sign up, signed up less than the control group. The cost of the experiment, in other words, is you lost about 20% of those subscribers just by experimenting on them. And of course, that loss is going to scale with this. If you run it longer, more units are going to come in. And I'm going to convert it to dollar amounts, or I'm sort of in the business school. They want to see what's the impact to the business. So in this sample, about 30,000 subscribers were lost. And this translates to $1 million that Netflix lost by running one experiment, okay? I admit this is a particularly harmful experiment. Many Netflix experiments that are harmful are like in the negative 1% ranges, but they really add up, right? Even this one sort of example here should be, oh, that just seems like we could do better. And I want to give a very quick peek. If you do our method, you can still learn this, but you only lose $60,000, okay? And this is precisely why Netflix is interested in doing things like this. So the motivation here, and like I said, I'm at the very end of the motivation, and I spent quite a bit of time on it, but I wanted all of us to be very clear that what we're trying to do in this project here is continuously monitor, and I'll be precise about what this even means, but really to stop this early so that we don't lose this much money. Just to quickly end on the introduction, I want to give a very short slide on the scale of this issue and why it's relevant today. So if you're sort of in tech, you have to understand that this scale of this data and experimentation is growing exponentially. For example, the numbers are like 10,000 A/B tests annually, and this is not an NDA violation because you can actually see this number in their blogs, right? And I think Google and Bing are running like 100,000 A/B tests per year, so in the 6 digits. There are, of course, papers out there that show like, hey, if you don't do experimentation, basically you lose 100% of revenue compared to firms that do experimentation. So many of these firms know that experimentation is super important, and if they don't, they're losing out. In fact, Netflix, where I sort of interned, they have an entire team called the experimentation team, an entire self-made platform called Ablaze, where they're running this not through a third-party software or anything, but an entire dedicated horizontal team to make sure that everybody in Netflix across every single team can experiment, okay? So the goal here, given how large the scale and how important this is to many tech companies, is we want to be efficient, okay? We don't want to run it for 1 billion weeks. We want to ideally have some automation, just run it and stop based on some automated stopping rule. This will be a bonus. But really, like I was saying, we want to have some risk mitigation, okay? So we want to stop those negative experiences early, and this is exactly what this talk is going to achieve. I'm going to stop here and see if there's any questions. Yes?
If the size is large, should we expect to stop sooner?
Exactly correct.
That's the bonus.
Exactly, and I'm glad you asked. And it is true, though, that these things here, how fast you're going to stop is indeed a function of this negative 20%.
Yeah.
If you can't detect a really big effect, for example, let's just make this negative 0.001. It's unlikely you can stop early because it's really hard to detect that effect. So it will scale with this, and you actually see this mathematically. Great. Just going to pause for 10 seconds. Okay. So we are not the first ones to actually do anything like this. And even before I go into the literature review of, sequential methods, anytime valid methods, I want to talk about what do they even do in industry, like at Netflix. If you walked into Netflix, maybe 2 years ago, before sort of me and many other people there wanted to bring this into their experimentation team, what were they doing? Because they probably know about this, right? They're not completely oblivious to this $1 million loss problem. First of all, they are doing t-tests, okay? Many of them are straight up just doing t-tests for the analysis, okay? So let's just first of all start with what they are doing to analyze the data. And I want to mention that the way they are doing this risk mitigation or the continuous monitoring part is this ad hoc peaking. I'm going to explain exactly what this means. But in statistics, this behavior of peaking is so common that there's a name called peaking. And basically what they do is they're scared that it might go crazy or their experiment is getting crazy, like this negative 20% treatment effect. So they check on day one, even though they actually said, we're going to run this experiment for 2 weeks. What do I mean by check? They actually run the t-test, they actually do the difference in means, and they do the hypothesis test. And then they say, so far, the confidence interval is not crazy. I'm satisfied with that. And they do it again in day 2 because they're scared. And then they wake up again and they do it in day 3. And I talk to some of these analysts, and sometimes they check multiple times in a day, okay? Because they're scared, right? They started an experiment and they just don't know. Sometimes these experiments are completely black box ideas, okay? So they're scared. I hope that many of you can see the problem with this peaking behavior. In fact, this is such an established problem in statistics. There's a whole name for it, or like sort of double dipping often, what it's called. And let me just show you through some very simple simulations the exact problem. Okay, I actually stole this graph. I made this myself, but this is from I believe Ramesh Johari's paper. But it's a very simple example. Let's just imagine that our data is X given from normal 0, 1. And all this means is that I have IID Gaussian data. Certainly my mean is 0. The mean is exactly 0. And all I'm doing is doing a t-test while I get more X data and seeing if my mean is 0. Okay. So in this case, we are exactly under the null hypothesis. In other words, in this case, the test that we're testing is true. The null hypothesis is true. The mean is exactly 0. So I should not be rejecting. And what the y-axis here is simply saying is how often do you falsely reject? Okay. So I understand that not everyone here is from the statistics community, but basically what this y-axis here is just trying to simply say is when you run an experiment, you want to have a safeguard for, oh, when we make this confidence intervals, is it truly covering the mean? And we create these probability guarantees. And the number one guarantee that every hypothesis test has to have is this type 1 error control. Okay, so that's sort of what you should think about when you think about exactly what I'm plotting here in the y-axis. In other words, if I basically have an alpha level of 0.05, I should never be rejecting more than 5% of the time when my null hypothesis is true. In this case, it is true. Let's see what happens when you do peaking. The x-axis is simply day 1, they check, day 2, they check, day 3, they check, and all of those data they're getting is simply exactly from normal 0, 1 IID. And they check them through a t-test, replicating exactly what Netflix person would do. If you see the blue line here, even in about 10 days of checking, in this row right here, you get almost a 40% type 1 error when you should be getting 10%. Okay, so this is a crazy inflation. If any statisticians see this, they would be like very unhappy with this. Okay. And what does it even mean for the business manager? It means they're going to think that there's some effect. You can imagine X just being the treatment effect. They're going to think that, oh, it's not a 0 effect, it's some true effect. And they're going to be like, oh, that ranking algorithm B is better. And they're going to make a lot of false innovations. They're going to be like, okay, let's ship off the ranking algorithm. Let's change this color of the button because they all think those experiments were successful. But it truly is not. This is a 0 effect mean. And they're just getting too many false innovations when people are continuously checking like this. Okay. So the solution that actually we do want to pause here to see if there's any questions about this. Yes. I just missed the last word, increase in what? Oh, yes, absolutely. So you want to just basically see why. This is a great question. So is exactly related to multiple hypothesis testing, okay? So you should think of it like this. Even though the data is truly from a normal 0, 1 and the mean is 0, because the t-test is valid if you test one time, there's about a 5% chance I could literally say there's some effect. That's what it means by this alpha level, is that there's a 5% chance. Now, if I ask you, and this is not truly independent, but if I ask you, there are 2 times you can check, and there are 2 times you can make a 5% mistake, I bet you'll see in the second time you have a higher probability of making a mistake because you tested it 2 times, right? Now, if I ask you 3 times, it gets only higher, right? 4 times, definitely, because each time you have a 5% chance to make a mistake. That's exactly the intuition. And you can see it doesn't scale linearly because these are actually dependent, because we're actually aggregating all the previous data as well. And that's why we sort of have this this tail behavior. It's a great question. Yes. Okay. So the suggested solution in the literature is called confidence sequence. Because people are aware of this. People are aware of this annoying sort of inflation here. So they want to know, how do we make sure we can actually keep these blue and red lines below their dotted blue and dotted red lines respectively, okay? And the solution to this is building confidence sequences that look something like this. And I'm going to go over this fairly slow, okay? Hopefully you should actually all know, before I even show this, what confidence intervals mean, okay? So the confidence interval has this definition. If this is a true triggering effect, so mu here could be like that 0. The 0 better be covered by what you create, the interval, with high probability, 1 minus alpha. That's what it means to be a confidence interval. And the most important thing is that this is true at some arbitrary point in time. Okay, so if I tested it at 500, then it's true. If I tested it again also at 400, it's also technically true. Okay, but it is not true if I tested it at t equals 400 and 500. That is the difference. What confidence sequence do is actually, you can see it's basically almost the same definition, but instead the V becomes a VT because it's a sequence of intervals, sequence of confidence intervals, and it will cover the truth, but uniformly at every time. So the fact that I moved this thing inside the probability statement allows these sort of blue and red line to always remain below like this. Okay, that's exactly what this mathematical statement on the top right is describing. I haven't even actually told you how to construct this. It might not be obvious how to even satisfy this, and I'll talk about that. But all I'm stating is a definition that I'm going to achieve to allow them to do this. So just to give you a quick preview before I go into the math, if you follow my paper and you do this confidence sequence, it looks something like this. Like I said, it's a sequence of these lower and upper confidence intervals. And it will have the property that at every time it is valid, okay? And of course, what can Netflix do? Keep in mind, this experiment ran on 20,000 units, okay? Even on day 1, on about 250 units, the upper confidence interval doesn't cover 0 and quite significantly is below 0. They can see the treatment effect is negative and very statistically negative, okay? It's not just a noise. So they could have just stopped it there. They could kill it right here. And there would be no validity, false discovery kind of problems. And that's exactly what I mean. If they killed it at around, I think the envelope calculation I said was if they killed it here, that would be the $60,000 loss. Okay, and this red line is what my paper will build. Okay, and this is exactly with these red contour lines, and this is actually what many Netflix experimentation team is doing right now. They sort of achieve these 3 goals that I mentioned before. Okay. Yes, so let's take this student question back. Yep.
There sort of confidence interval keeps going down this time goes.
You'll see this in the math, but let me explain it intuitively. Okay. So basically, as time and units for now can be almost interchangeable, and I'll explain the notation carefully later. But as we sort of go through time to get more people in our sample, if we get more people in our sample, we get larger sample size. This decreases variance, so we get even more sure about our treatment effect. That's the intuition. And you'll see this in the math, though, and the exact order in which it will decrease.
Why did you not stop as soon as like 0 outside?
Yeah, no, this is almost just like a practitioner kind of, you could, I mean, I think the idea of automation is they probably want to send a flag to the analyst as soon as they see a negative. And I think many analysts do that. I should double check with what they're doing now. The reason why is they're actually worried about non-stationarity. They're like, okay, I kind of want to see this stabilize a little bit. And I by 5 members, you see it's pretty stable, like it's pretty small too. Yeah. So that's the reason. It's more like a practical reason. Yeah. I'm gonna do my due diligence and not show that I am the first person to come up with these red contour lines that you see. There are actually many existing methods, and there's actually one person here that actually came up or works on these methods. But I do want to summarize very quickly that many of these methods do require sort of these IID assumptions or like a very simple experimental setting. Okay, but those solutions do exist. For those simple settings, they can create those red contour lines. Here's an example all the way back to the 1940s. Wald comes out with the sequential probability ratio test, which is completely parametric. And just as a very sort of a quick overview, there indeed is many recent advances. You can see these are very recent papers because actually a lot of tech companies are interested in these methods, and many of these are actually industry collaborations with like Adobe, Microsoft, and etc. But they do have many assumptions. For example, what I mean by model-based is they assume the response is binary with a logistic model. And here, they assume the outcome is completely bounded, for example. And many, if not all of these papers actually assume that the outcome is stationary and has some regularity assumptions that does not match Netflix. Okay, and I'm going to be very concrete about this. So Netflix came to us, or more precisely, my advisor back then at HBS, Yav. So Martin, he was the executive at the experimentation team, and he read these papers, or he had someone read these papers, these typical papers, and he said, the solution still doesn't exist for the problem I care about. And what was the problem he cares about? The experimented data looks something like this, where the majority of their experiments look like this. Why? You have N members, me, you, N, these 3 people. They want to see our behavior, our time watching on Netflix over time. This is called a panel data, or in Netflix, they call it member-based experiments. And this is by far the most common experiment at Netflix. Okay. So again, this is an N by T matrix because they choose N customers they want to experiment on, and they observe them across some time. You can imagine, just look at this data set and think of why me, I think their primary metric is my time spent on the platform, okay? If I told you I spent a lot of time today, I bet you'll realize that the time I spent tomorrow is very correlated. I could be in the middle of the show, okay? So then tomorrow I'll watch it again. And so is the third day, right? You probably have these blocks of time. So any of these so-called independence assumptions or these treatment effects, or even the estimate being defined on some IID population just cannot work for their setting, okay? And they also do a lot of these adaptive experiments where they're changing the probability of treatment assignment. It does indeed exist solutions to this, but the combination of these are very tricky, okay? But they do have many of these more non-standard, not just like a simple coin flip 50-50 kind of experiment, but they have much more dependency, much more complex experiments. And our paper really is going to solve all of that, okay? So this is sort of going to be my one slide contribution summary. But the main motivation here is we're going to construct these confidence sequences. That's what I mean by CS, these sort of red contour lines for these complex settings, okay? Finally, sort of solving that need in these member-based experiments. And I'm going to do it with minimal assumptions. Why? Because if I have many assumptions, it's not going to work for these, non-stationary settings as such. So the proposed main result that I'm going to say is not only going to be valid for all complex experiments, but really I'm going to do this through this non-parametric statistics way, through inverse propensity score estimators, and through asymptotic results. Okay? And I'm going to get into the nitty-gritty of this after this slide. Is there any questions? I mean it generally. I do not mean it mathematically. I'm not stating complex equals non-IID or anything. I think I'm just generally stating that Netflix has these many complex experiments. And what I mean by complex is sort of experimental settings like the panel data, the panel data settings like here, where the typical assumptions just don't work. But that's not a mathematical definition. Yeah. So before I go into the main result here, I want to just quickly review one key important tool that sort of we need to achieve this, okay? So I said this definition, and I haven't even told you how to build it. Okay? It's not easy to build, and if you think about it for just a second, similar to the question that was asked before, this is kind of like a multiple testing question. If you test 1 time, 2 times, 3 times, each time you have some chance of getting it wrong, but you want to bound all of those chances you get wrong uniformly. And actually, this is going to go to infinity, not just for every t from 1 to some big T where big T is bounded, but this has to hold if they want to check it infinitely. It's quite a stringent condition. In fact, if you test it infinitely, it's not at all obvious you can even achieve this. Okay. So on that note, before I introduce the tool, I'm going to just quickly state that if we have a 2-sided t-test confidence interval, this looks exactly like this, and hopefully this should be familiar without explaining any notation. The other question that we're going to ask ourselves to achieve this blue VT in the stringent definition above is we know this here is not good enough. This is a confidence interval. Why do we know it's not good enough? Because of that graph I showed you with the PK. This is just not wide enough to cover these sort of false chances we can get wrong every time. So we know we need to make it bigger, okay? And you should think of n as t, okay? So as n sort of scales across time, sort of as we get more and more data, we cannot just scale it with square root of n or 1 over square root of n. We need to somehow inflate it and make it bigger so we have this much more stringent definition satisfied, okay? So just keep this in mind as I explain my results, and I'm going to further come back and explain what this f of n has to be, okay, or the order of f of n. Great. But just to get back to this question, the way people actually construct this this VT to satisfy this very stringent probability constraint, it turns out that this seminal sort of French guy right here came up all the way back in the 1939, a very important inequality called the Weil's maximal inequality, that states that if you have a non-negative super martingale, then you can immediately get this probability constraint satisfied. And I don't think I need to do any translation here because this is just this. So you can actually directly get it as long as you build this. So basically, there's even a paper actually by Aditi Arandas that shows that all confidence sequence or all admissible confidence sequence are basically martingales, okay? So you have to build martingales to do this. And this is the tool that we're going to use. I'm not going to go into the proofs or anything deeper than this statement here, but hopefully you've learned that in case you're curious, how do I even do this? This is the tool, this martingale technique. And now I'm going to switch gears a little bit and explain the causal inference part to finally give the last missing piece to build my estimator, my sort of final result, excuse me. So we're going to actually rely on design-based causal inference. And I understand that design-based causal inference might not be familiar to everyone, but you should just immediately think that this design-based, what that means is simply we're going to use minimal assumptions and only focus on inference on our sample, but really through the treatment. Okay, and it might not be obvious what that even means, so let me just show it through math. Let's assume right now we don't have the n by t panel data, but we just have sort of a stream of individuals coming. You turn on the sign up page and there are n people coming in across time, okay? So let's say you're the first unit, so that subscript is just I. You can be in treatment or control, 0 or 1. And in causal inference, I'm going to use the potential outcome language. You have 2 sets of possible outcomes. Your engagement on Netflix, if you got the treatment, or your engagement in Netflix if you didn't. And in design-based causal inference, these are constants, okay? They're not random. They don't even have dependencies, these potential outcomes. So you can already kind of see how I'm solving stationarity here. These are just completely fixed constants, okay? In case you're curious, the superpopulation view or the other view, not design-based view, would make them random and coming from a distribution, IID from some distribution P. Does the observed outcome, because you don't actually observe both of them, right? You only observe, for example, if you are I equals 1, and for example, you're in the treatment, you only observe this. Okay? So the observed outcome here is going to be yi1 times wi plus yi0 times 1 minus wi. If you get into the treatment, you observe this one. If you get control, if you put 0, you'll get this one. Okay? And the estimate, or the thing that we're covering, is some sample ATE stands for average treatment effect. Okay. And this simply means if I have n people in my sample, I'm just going to estimate those n people's treatment effect mean. I want to very clearly state that this is non-parametric. In other words, I'm not making any assumptions on the population. In fact, what is a parametric assumption is the more typical counterpart that looks like this. This might seem actually more innocuous and less assumption-like at first, but as soon as you put an expectation, you need to define a random sample. And what they do is they're saying all the people here are just coming from IID samples from some distribution. Okay, so this is not the estimate that we're going to focus on. Okay. And this also allows risk mitigation, because if you think about what it even means to have a risk or a harm to Netflix, what does it even mean to say I lose $1 million? It means that these real people here, not from some infinite population, but these real finite number of people had some loss. Okay, this point is fairly subtle, but the more I think if you do sort of think about it and yourself, you realize that the first estimate is much more conducive and sort of matches with what Netflix wants when they want to figure out how much money did I lose or something like this. I'm going to go over this part fairly quickly, but the estimators that I use, given the notation I've defined, is actually just going to be the simple inverse propensity score estimators, or they're also known as the Horace-Thompson estimators. And it's simply just going to take the response at each individual and reweight it by their probability. Okay, so this here is just usually 50% if you're just a fair coin flip between 0 and 1. I've actually made these probabilities also fully adaptive. This filtration means every data in the past. So in case Netflix was actually changing these probabilities, that is also okay. Okay, so they could depend on the past. And this is simply just the variance, corresponding variance estimator. So there does require assumptions, and I want to be clear about that. So the two main assumptions we use in our paper is the first very relatively mild assumption called positivity. It just means that basically everyone can be in the treatment group. Okay? It just means that there's some probability that everyone can be in the treatment group. Otherwise, this denominator here becomes 0. So this is just not good. And the second assumption is a little more subtle, but we will assume some bound on our outcome, but we will assume that most importantly, this is on the realized outcome. For example, if Netflix assumes an infinite population, I'm not saying that every single infinite number of them has to be bounded by m. It just means if I had 10,000 people in our sample, those 10,000 people don't have an infinite outcome. And this n can be a billion or even a trillion. Okay, and it will not affect our main result. By the way, for Netflix, metrics and outcomes, all of their outcomes are almost categorical. Like it's just 1, 2, 3, 4. Many of them are binary, like 0, 1. So that will immediately satisfy us. Immediately. The last missing piece, and I'm going to sort of skip this by just relying on this very nice paper, is that we're going to build asymptotically valid confidence sequence. And the way you should think about it, because technically I only define confidence sequence in finite samples, but you should think that definition is satisfied after enough time. If you're curious exactly how they formalize the mathematics of enough time, there's this paper here defines this for me, and we use exactly their definition. Okay. But you should think of this basically like the asymptotic confidence intervals, right? Like the z-test, t-test, they're all asymptotically valid when the data is not exactly normal. This is kind of just like that. Yes?
You need to know n.
No, for our main result. This is very important. So if m is 1 trillion, our results will not scale with 1 trillion. for our main asymptotic result, but not for our exact result. And you'll see this later in the math. Yeah. Okay, I believe I've explained all of the main ingredients to actually, oh, we're a little short on time, to actually explain my result. But the result is sort of just this one result, so I think you're gonna actually explain it. But this is the main result here, okay? This expression here finally builds that those red contour lines that are valid. And the theorem is simple. It's basically saying if you build those red contour lines with this expression here, then you are asymptotically a valid confidence sequence. Okay, it's basically saying you are getting the right uniform coverage probabilities. Right. It is not super important for me to actually go through each and every single one of these terms, so I'm gonna spend only a few minutes here to emphasize 1 or 2 points. I'm not going to talk about impact data, but let's return to this question. To achieve this confidence sequence, you might ask, what was the penalty I paid? How much more did I have to make the width bigger? Because people might be like, I just want to do this. And if you're telling me to do this, I have to make it bigger. And then their natural question is, how much did I lose? How much bigger did I have to make? And I'm going to answer this question through an asymptotic order analysis. Okay, so we're just going to focus on what is the order complexity as we make the samples larger and larger. If this is the variance, by the way, this is the actual width. The n, 1 over n here is the, I'm just focusing on terms that scale with n. Sn is another term that basically has n variance terms, and everything else are just constants except this. So we have 1 over n, an order n, and an order n, a log order n term here under the square root. And you can actually see that this is roughly, this is actually exactly of this order. This f of n term is exactly of this order, okay? Or more precisely, excuse me, the entire variance term is of this term. So the f of n term is about a log n term. So I've paid about a log n factor to make this confidence sequence valid at every time. That's the deal. And that's not bad. Log n's are not bad. It's not polynomial at least. Or even worse, imagine this f of n was square root of n or above. And these things cancel, or it gets even bigger. That means as you get more and more data, you're getting more and more unsure about the treatment effect. That would be terrible. So it's good that we've sort of achieved the desirable rate. I'm going to just very quickly go slightly to your question. What if I don't like asymptotic results? Keep in mind this is valid after some sufficiently collected data. If you don't like asymptotic results, this is another result in our paper that shows that this is exactly valid. And if you look at these constants here, I'm going to go the 2 things, is that this little n here scales with big M and that epsilon that you were talking about, okay? So the P min is the absolute minimum propensity score. And I think you can also sort of guess, but the reason in every sort of exact, there's no way around this, because in exact results, we have to account for worst case variance, and worst case variance will scale with the worst case, possible maximum and possible minimum. And this would really suck if you say your outcome is super continuous and you have this one person whose outcome is 1 billion and everyone else is 1, then the big M is 1 billion. It becomes really large. Number 2 is actually the order in which this shrinks is not even asymptotically going to 0, because Sn, keep in mind, is order n. So this actually shrinks to a constant, okay? I have been able to fix this with the help of some very nice collaborators in the DTS group too, to make this order shrink asymptotically to 0, but at least this closed form solution does not work. A non-closed sort of iterative root solving algorithm can make this go to 0. Just going to pictorially demonstrate this, and it's not super important for us to go through the sample, but this is my main proposed algorithm. In 10,000 samples, it is going to 0. It's hard to see, but it keeps shrinking as you get more data. In the exact version, it just stabilizes to a constant, even if you get more data. But it's still useful. Like if you have enough signal, you'll still see a treatment effect. And it's exactly valid. Like you don't have to wait for some time. Okay, I'm going to spend just maybe 2 or 3 minutes talking about this final point here, which is I actually haven't so far talked about that complicated panel or member-based experiment. Remember, motivated this whole talk about solving complex experiments? I haven't at least directly dealt with that part yet. And I'm going to explain how this sort of very smoothly works. Just look at the assumptions that I've stated in the theorem. There's nothing about the dependency of Y. There's nothing about the stationarity. There's nothing even about IID. Because remember, assumptions were two, sort of the positivity one is basically saying everyone can get the treatment and their outcomes are not like 1 billion. Or even any distributional restrictions on the treatment assignment, except the fact that it cannot be 0 or 1, right? It can handle even adaptive experiments. So this theorem actually holds for more sort of non-IID data. And that's really it. I've kind of worked out the math where I've changed notation. I've added the n comma t, but basically this would work exactly for that if you do that sort of trick and make it work for the time series data. But this would be the exact same expression. So like I said, if you have time series data, you can imagine things are much more complicated. Instead, we have sort of n units arriving. Now we can have 1 unit we're experimenting on across time. This is what Uber does all the time. And in there, they don't even allow the potential outcomes to depend only on their current time. It has to depend on everything in the past. This can also be handled in our framework. And of course, member-based experiments, the way it works is you have n time series. If I can solve this, I just collapse the time series through an aggregation trick. And now I have 1 time series with sort of n by t. So if I can solve this, I can solve this. Okay. That's the extent to the details I want to say of solving complex experiments. Great. I think I'm going to skip this. So just want to show applications. It was better. I tried it on their data. It was better. You can find things much faster and save money. Okay, so that's sort of the takeaway message for the applications. And the last thing I might say is the whole talk so far have been motivated by, oh, we have these complex experiments. We have things that sort of don't work in IID. But what if things are truly IID? You know, what if they want to actually utilize those utilize the power of the extra assumption that we have IID? Because right now I didn't. And of course, you have more assumptions, you can get better results. I wrote another paper with actually the same set of co-authors. It's under review at JASA, where if you just run a linear model under these IID assumptions, you can get a much tighter confidence interval. And all of these numbers here are just, if you run the linear regression, are just OLS coefficient, OLS standard error, and OLS design matrix. Basically, this is very practically attractive for Netflix because they're already running linear models and they can get all of these from an engineering perspective directly from the model and easily pull them out. Okay, and this would be valid under exactly valid for your linear model and non-parametrically valid asymptotic. And that's what we proved in this paper. I think that's it for, like I said, these 2 papers are indeed implemented on their Netflix experimentation team since two-ish years ago. I spent my, internship last summer actually going on their platform, going to the engineers and coding some of these up. And not every team is using it. Like some of these people still take convincing, you know, they don't believe, they always ask me like, why are these widths bigger and such? But many people have been convinced and are using this to stop experiments earlier right now. And I believe not just Netflix, Facebook, Google is starting to get Google is already doing this. Facebook is starting to get interested. And this is very much an exploding field in tech. I recently got a puppy, so here's my puppy, and I was just curious if you guys all had questions. Thanks so much.
Yes.
Yes.
Is that a typo? Like, should it be square root of log n?
Oh, it was basically like square root of log n, and we just basically chose that as log n. These are like very minute differences, but you're technically correct. Yeah.
Is it true that the optimal rate should be? I don't know about asymptotic CS, but should it be the like?
That is exactly correct. So I think what you're referring to, just so we're on the same page with the audience, is this rate that we're talking about or the penalty term that we should add. There is an optimal penalty term. I'm not technically at the optimal penalty term because it's log, but I'm at the log level, not the second log. Yes, that is correct. Yeah. But your theorem in theory is exactly correct. Yeah.
Second is in practice, like how do you deploy like asymptotic CS? Like what is the meaning of log enough? Like
Yeah. I've been asked this question. This is why I think I always have to provide this exact result. Otherwise the reviewers won't be happy. My honest answer is kind of similar to what they're doing already. You know, their z-test and t-test are asymptotically valid. Technically, they wait longer, right? So our anytime valid method, they could literally do it with 3 data points. What I end up telling the analyst is, hey, don't do it in 3 data points. Can you at least wait for like 50, 100, you know, the super general rule of thumb. But Netflix, their data sets are pretty big. Like they turn on the experiment and in probably about 5 minutes, they get over 100 people. So I think they're not super worried about the asymptotics kicking in too late or stuff. But of course, from an academic standpoint, I don't think there's a true mathematical answer. And I've shown extensive simulations under like Gaussian and of course non-Gaussian, super skewed Cauchy data. It really seems okay. You don't have to worry about this being like, oh, when n is really small, you have crazy. It doesn't actually happen. I'll give you one more quick answer. Is because in the very beginning, the confidence sequence is the largest. So you're not really making false discoveries back then. Yeah. Yes.
Question is like, let's say if a population, for example, you got one region which is watching TV earlier, to a different like outcome, I guess.
Can you just repeat the question?
So like for Netflix specifically, let's say you have one region that wakes up earlier, has like a separate response to an experiment, versus the second region, I guess, starts using the experiment later.
Oh, so are you saying what do they do when they have these like multi-region, multi-time points experiment kind of thing? Oh, so they would, I don't think they actually do that. In other words, for example, this one experiment, I might be violating my NDA agreements here, but this one experiment that I showed you in the very beginning was only performed in Mexico. And they usually do not do across countries, or they usually just start it in one go. Now, there are cases of staggered adoption. Basically, they turn on the experiment and people come in later, or they adopt a treatment later, they come into the experiment later. But I don't think that's fine, but I don't think they would do it across like, I'm just going to do it in another region. And I certainly don't think they would change their outcome in that way. They will still keep tracking engagement on Netflix or other metrics. Yeah. Yep. Great. Thank you so much. Any more questions? Yeah. The LIN